All right. So the last time we were talking about dating, figuring out how old the Earth is from radioactive substances that we find on the Earth. And one example here is is potassium 40. Potassium 40 has a really long half life. It's one point two eight billion years. So basically every 1.28 billion years, it's kind of hard to say. Um, half of the potassium, the radioactive potassium, turns into other things. Okay, so it turns into calcium and argon. Um, so with rocks, for example, you don't normally find argon in rocks, right? Remember, argon is one of the noble gases, and it doesn't, chemically, the noble gases stand alone. Helium and neon and so forth. They don't bond with anything chemically. Um, so when we open up, when we analyze these rocks that have potassium 40 in them, um, and we find argon, basically the ratio of potassium 40 that is in the rock versus and the amount of argon and also the amount of calcium, but that just makes it more complicated. But I mean, it can be done, right? It will allow you to figure out how old the rock is. All right. Here, let's. Oops, I went the wrong direction. So that's that's one of the things that people do is that they'll take these rocks and we figured out, for example, that the Earth is 4.5 billion years old. Not just that, of course, we get rocks from the moon. There's nothing in the solar system that is older than 4.5 billion years. All right, so that tells us pretty much that the entire solar system began 4.5 billion years ago. All right, and here's a simpler story. All right, so potassium 40, that's wonderful, and the problem is it breaks into these other things, and it just makes it more complicated, right? I mean, the argon that's if it just became argon, that would be nice and easy. All right, so now there's a substance, of course, called here. Let me. I think I have it here. Where is that? No, not this. This. Okay. So, of course, yeah. I mean, everybody's heard of uranium, but there's a type of uranium that's the most common type of uranium that is found on the Earth. It is called uranium 238. All right. So that's a particular type of uranium. That's not the type of uranium you can make bombs with or anything like that. All right. Now you just like the potassium 40, uranium 238 turns into other things. Okay, um, but see, the other things that the uranium turns into are also radioactive, right? But eventually the uranium 238 leads to what are called daughter atoms, and then the daughter atoms will eventually become lead 206. And that's really stable. All right. So that's an extremely stable type of lead. All right. So this is a good way to think about this story. All right. So if you look, the half life of uranium 238 turns out to be 4.5 billion years. All right. So keep that in mind. For the amount of time for the uranium 238 to turn into turn into one half life, right? So you start with a certain number of atoms of uranium 238. You wait one half life, you're going to have half uranium 238 and half lead 206. Again, lead 206 is extremely stable, right? It's not radioactive, and we use that all the time. All right, so let's go back to our slides here. So now I know this talks about potassium, but we do the same kind of thing with other radioactive substances that have really long half lives. So uranium 238, right? when you dig up some uranium ore, let's say, and you find that there's uranium-238 in the ore, um, and you do a further analysis, just like we did with the rocks that contain potassium-40, but you do the further analysis, and you find that um, that in that rock in that rock that contains the uranium 238 ore, there is lead 206, and it's not just any ratio of lead 206, right? That's the key. So there's exactly half, right? So one half life. Now for lead 206, sorry, for uranium 238, one half life is 4.5 billion years. So for you to get like half of the ore to be uranium 238 and half the ore to be lead 206, right? One half life, which happens to be the half-life of, again, the half-life of uranium 238 is 4.5 billion years. So that tells you that particular ore sample is 4.5 billion years old. All right, so now that's fine. Like you dig up some uranium ore, and you find half of it's lead and half of it's uranium. All right, so now you might say, okay, that rock is 4.5 billion years old. And by the way, what I'm telling you is it's much more complicated, but eventually this is what this is how we figure this kind of thing out. All right. So with one sample, you can't say anything about the age of the Earth, right? There's no way, because you could, let's say you find another sample and there's, little less than half of what's remaining is the uranium 238, right? So then more than one half life has gone by, right? But so here's the key, right? This is the key part about this. So here, let me go back to this picture here. This thing that I had. Where is it? It's right here. So everywhere, all right. This is really an important idea. Everywhere on Earth, when we find uranium 238, it's always in a 50-50 ratio of uranium 238 and lead 206. Always, never an exception. So you think about it, like we've dug a lot of uranium out of the Earth, right? And everywhere, all across the planet, there's always a 50-50 ratio. And the moon rocks that we have, 50-50 ratio. The Mars rocks that we have, a 50-50 ratio. Anything we ever find in the solar system, and we can perform this experiment, you always get a 50-50 ratio of uranium 238 to lead 206, which tells you that there's been one half-life gone by in the solar system. All right, so that's that's an important point, right? That's an extremely important point. That's how we know that the Earth is 4.5 billion years old. And again, not just the Earth, everything else. All right. Now the Earth is an active world, and we're going to find as we tour the rest of the solar system that's not always the case. We talked about how the interior of the Earth is hot. Two reasons, just to remind you: gravitational squeezing, all the pressure that the entire mass of the Earth crushing down on the core, that causes the interior of the Earth to be hot, as well as radioactive material like uranium 238, right? That we find in the Earth, right? So because it's hotter in the core, and it's actually really hot there, close to 6,000 Kelvin or even more, a little bit more than that, we estimate. there are what are called convection currents that rise up. Like a convection current would be, for example, if you were boiling water on the stove, right, and you watch, as the water boils, it begins to bubble. There's these convection currents that take place between the cooler top of the surface and the hot part of the stove, and so you get these convection currents. And so that happens with the Earth as well. These convection currents rise up through the magma, and sometimes will actually go all the way up into the crust. Right. That's it, and of course, sometimes it does that violently. There's shaking, and that's what causes that. That's one of the things that can cause earthquakes. All right, so here's the example of oh, because I had a slide that shows this. This is a good example of convection. You have hot material rises. Hot stuff always travels from hot to cold, right? And so it rises up, and the colder stuff will fall, and then be heated up again, and so forth, right? That's the idea of a convective current. Right? So that's a good example in liquid. Again, this happens on the Earth as well. And as it says here, these are really slow, until there's, maybe a sudden movement of rock, and that's when you get sometimes volcanic activity, when this stuff breaks through the crust. Sometimes there's earthquakes as well. And the surprising thing is when there's volcanic activity, whatever the Earth's magnetic field is doing at the time. Now you might say, well, the Earth's magnetic field has always been the same. It turns out it hasn't. The Earth's magnetic field kind of wanders. So what is the north magnetic pole can sometimes be the south magnetic pole over geological time, as we're going to see. But that information gets frozen, if you will, in the volcanic the lava that solidifies, and you can see like little pieces of iron that line up with the direction of the magnetic field in the past. All right, so this is a good example of this convection, and so when this getting to what are called plate tectonics. So the crust of the Earth has different plates all over. There's another slide that will show this. And when the plates separate, that's called rifting, right? So they move apart. When one plate goes underneath another, and this happens near the coasts a lot. This is responsible for mountain building, where one plate falls beneath another. That's called subduction, right? And so you drag this rock down, underneath this other convective current that's going up. All right, so one piece slips underneath another, and that's what we like. If you ever notice, along the coast of California and Oregon and Washington and the western coast of Canada, of course, that's where the Rocky Mountains are, right? The Rocky Mountains, and then on the eastern coast, of course. Well, not exactly the coastline, right? But near the coast, relatively near the coast, I guess I should say. Of course, on the east side, we have the Appalachians. The Appalachian Mountains are much, much older, for example, than the Rockies. The Rockies are still forming; they're still rising. The Appalachian Mountains are getting smaller and smaller with time. All right, so we'll talk about plate tectonics in the next slide.